Hello everyone, I am Azak, a talkative data scientist, and I will be walking you through this Jupyter notebook written in Python. In the first code cell, we are importing the necessary libraries and modules for our project. We are using the OS module to access the input files, and we are using the sklearn.cluster module to perform cleans clustering. We are also importing pandas and min-max scalar from sklearn.preprocessing. Finally, we are using the warnings module to ignore any warnings that may arise during the execution of our code. Moving on to the next code cell, we will be importing the dataset and performing some data preprocessing. In this code cell, we are simply providing a brief description of the columns present in our dataset. These columns include dates, category, descript, day of week, PD district, resolution, address, X, and Y. The dates column contains the timestamp of the crime incident, while the category column contains the category of the crime incident, which is our target variable. The descript column provides a detailed description of the crime incident, and the day of week column contains the day of the week on which the crime incident occurred. The PD district column contains the name of the police department district, and the resolution column describes how the crime incident was resolved. The address column contains the approximate street address of the crime incident, while the X and Y columns contain the longitude and latitude coordinates of the crime incident. In this markdown cell, we are providing a brief summary of our project. Our project involves using the San Francisco crime dataset to perform map-based geographic clustering using k-means clustering. We will be using the longitude and latitude coordinates of the crime incidents to cluster them into different groups based on their geographic locations. In this code cell, we are reading in the San Francisco crime dataset using the pandas read_CSV function and storing it in a data frame called df. We then use the head function to display the first 5 rows of the data frame. We also provide a brief description of each column in the dataset, including dates, category, descript, day of week, PD district, resolution, and address. Finally, we mentioned that our goal is to create a map-based geographic clustering of the crime incidents based on their location in different districts of San Francisco. In this code cell, we are using the dtypes attribute of the pandas data frame to display the data type of each column in the dataset. As we can see, most of the columns are of object data type, which means they contain strings. However, the X and Y columns are of float64 data type, which means they contain floating point numbers. This information will be useful later on when we plot the crime incidents on a map using latitude and longitude coordinates. In this code cell, we are dropping some of the columns from the data frame that we will not be using in our analysis. We use the drop function of pandas data frame and provide the list of column names that we want to drop. We set the axis parameter to 1, which means we want to drop columns instead of rows. The columns that we drop are PD district, address, resolution, descript, and day of week. We only keep the columns dates, category, X, and Y, which will be used for our analysis. In this code cell, we are simply calling the head method on our pandas data frame df. This method returns the first 5 rows of the data frame by default. As we can see from the output, our data frame has 4 columns, dates, category, X, and Y. The dates column contains the date and time of each incident, the category column contains the type of crime committed, and the X and Y columns contain the longitude and latitude coordinates of the incident location, respectively. This is just a quick way to get a glimpse of our data and make sure everything is loaded correctly. In this code cell, we are calling the tail method on our pandas data frame df. This method returns the last 5 rows of the data frame by default. As we can see from the output, the last row in our data frame is from January 6, 2003. This dataset contains crime data from San Francisco, and it looks like the data spans over a decade. Again, this is just a quick way to get a glimpse of our data and make sure everything is loaded correctly. In this code cell, we are calling the isNull method on our pandas data frame df, which returns a data frame of the same shape as df but with Boolean values indicating whether each element is missing or not. Then, we are calling the sum method on this Boolean data frame, which returns the number of missing values for each column. As we can see from the output, there are no missing values in any of the columns. This is important because missing values can cause issues with our analysis and modeling, so it's always a good idea to check for them before proceeding. Next block will be Markdown cell. In this Markdown cell, we have a brief description of what we will be doing in the next code cell, which is a filtering operation. This means we will be selecting a subset of the data based on certain criteria, such as a specific date range or category of crime. Filtering is a common operation in data analysis and can help us focus on specific aspects of the data that are relevant to our analysis or research question. Now, let's move on to the next code cell and see how we can filter our crime data. In this code cell, we are filtering our crime data to only include data from the year 2014. First, we define a lambda function f that takes a row of our data frame as input and returns the date portion of the dates column. We do this by splitting the dates string on white space and taking the first element, which is the date. Then, we use the apply method on our data frame to apply this function to each row of the dates column. This replaces the original dates column with a new column that only contains the date portion of the timestamp. Finally, we use the head method to display the first 5 rows of our filtered data frame. As we can see from the output, the dates column now only contains dates from 2014. This is just one example of how we can filter our data to focus on specific aspects of interest. In this code cell, we are converting the categorical variables in our data frame into numerical variables using one-hot encoding. First, we use the get_dummies function from the pandas library to create a new data frame with one-hot encoded columns for each unique value in the day of week and PD district columns. Then, we use the concat function to concatenate this new data frame with our original data frame, effectively adding the one-hot encoded columns as new features. Finally, we use the head method to display the first 5 rows of our updated data frame. As we can see from the output, the day of week and PD district columns have been replaced with one-hot encoded columns. This is a common technique used in machine learning to convert categorical variables into numerical variables that can be used in models. In this code cell, we are using the tail function to display the last 5 rows of our dataset. This function is used to view the end of the dataset and can be helpful in identifying any patterns or trends that may be present towards the end of the data. As we can see from the output, the last 5 rows of our dataset show the year 2003 and the corresponding crime categories and locations. The X and Y columns represent the longitude and latitude coordinates of the crime location. This function is useful when we want to quickly check the end of our dataset without having to scroll through the entire dataset. In this code cell, we are creating a new dataframe df_2014 that only contains the rows where the dates column is equal to 2014. We are using Boolean indexing to filter out the rows that do not meet this condition. After creating the new data frame, we are using the head function to display the first 5 rows of the new data frame. This function is used to view the beginning of the dataset and can be helpful in identifying any patterns or trends that may be present towards the beginning of the data. As we can see from the output, the new data frame only contains rows where the year is 2014 and the corresponding crime categories and locations. The X and Y columns represent the longitude and latitude coordinates of the crime location. This code cell is useful when we want to create a new data frame that only contains a specific subset of our data based on certain conditions. In this Markdown cell, the text scaling is written. This could be a reference to the process of scaling data in machine learning, where we adjust the range of our data to be more consistent and easier to work with. However, without any additional context or code, it is difficult to determine the specific meaning of this text. In this code cell, we are performing scaling on the X and Y columns of our df_2014 data frame. Scaling is a common preprocessing step in machine learning that involves adjusting the range of our data to be more consistent and easier to work with. First, we create a min-max scalar object called scalar. This scalar will be used to scale our data to a range between 0 and 1. Next, we fit the scalar to the X column of our data frame using the fit function. This calculates the minimum and maximum values of the X column, which will be used to scale the data. After fitting the scaler, we use the transform function to scale the x column and create a new column called x_scaled in our data frame. We repeat this process for the y column, creating a new column called y_scaled. Finally, we delete the original x and y columns from our data frame since we will be using the scaled versions of these columns in our analysis. Overall, scaling can be an important step in preparing our data for machine learning algorithms, as it can improve the performance and accuracy of our models. In this code cell, we are simply displaying the first few rows of our df_2014 data frame using the head function. This allows us to quickly check that our data has been loaded correctly and that our scaling process has worked as expected. The output shows the first 5 rows of our data frame, including the dates, category, x, y, x_scaled, and y_scaled columns. We can see that the x and y columns have been successfully scaled to values between 0 and 1, and that the original x and y columns have been removed. This is a useful step in our data analysis process, as it allows us to get a quick overview of our data and ensure that everything is working as expected before we move on to more complex analysis. In this markdown cell, the author is indicating that they will be using the ELBO method to find the optimal value of k for their k-means clustering algorithm. The ELBO method involves plotting the within cluster sum of squares, WCSS, against the number of clusters, k, and selecting the value of k at the elbow of the curve where the rate of decrease in WCSS slows down. This is a common technique for determining the optimal number of clusters in k-means clustering. In this code cell, the author is commenting that k is a hyperparameter that needs to be manually set by the user. This means that we need to choose a value for k that we believe will result in the best clustering of our data. The optimal value of k can be determined using techniques such as the ELBO method, which we will be using in the next few code cells. This comment is important because it highlights the fact that k-means clustering is a type of unsupervised learning, which means that we do not have a predefined set of labels for our data. Instead, we are trying to group our data into clusters based on their similarities and differences. The value of k determines the number of clusters that we want to create, and it is up to us to choose a value that makes sense for our specific dataset and analysis goals. In this code cell, the author is creating a range of values for k, which will be used to test different values of k for the k-means clustering algorithm. The range is set from 1 to 15, which means that the algorithm will be tested with k values ranging from 1 to 15. The author is also creating an empty list called list_dist, which will be used to store the within cluster sum of squares, WCSS, for each value of k. The WCSS is a measure of how close the data points within a cluster are to each other, and it is used to determine the optimal value of k. The author is then using a for loop to iterate through each value of k in the range. Within the loop, the author is creating a k-means model object with the current value of k, fitting the model to the scaled x and y coordinates of the data, and then appending the model's inertia, WCSS, value to the list_dist list. It is important to note that the author is using the scaled x and y coordinates of the data to fit the model, which means that the data has been pre-processed to have a mean of 0 and a standard deviation of 1. This is necessary for k-means clustering because the algorithm is sensitive to the scale of the data. If the data is not scaled, variables with larger ranges of values will have a greater impact on the clustering than variables with smaller ranges of values. In the next code cell, the author is creating a plot to visualize the within cluster sum of squares, WCSS, for each value of k. The plot will have k on the x-axis and the WCSS on the y-axis. The author is using the matplotlib library to create the plot. Within the code cell, the author is first creating a figure object and an axis object using the subplots function. The author is then plotting the values in the list_dist list on the axis object using the plot function. The author is also setting the sticks on the axis object to be the values in the range of k that was created in the previous code cell. Finally, the author is adding a title to the plot and labeling the x and y axes. The title of the plot is ELBO method for optimal k and the x-axis label is number of clusters, k, while the y-axis label is within cluster sum of squares, WCSS. In this code cell, the author is creating another plot to visualize the distortion value, inertia, for each value of k. The author is again using the matplotlib library to create the plot. Within the code cell, the author is first setting the x-axis label to k and the y-axis label to distortion value, inertia, using the zLabel and uLabel functions. The author is then plotting the values in the list_dis list on the plot using the plot function. The x-axis values are the values in the range of k that was created in the previous code cell, and the y-axis values are the corresponding distortion values. Finally, the author is displaying the plot using the show function. The author has also commented that they will be using k=5 for the clustering algorithm. In this markdown cell, the author has commented out a block of code that they do not want to run. The code block is creating a range of values for k and then using the k-means algorithm to fit the model to the data for each value of k. The within cluster sum of squares, inertia, is then calculated for each value of k and stored in a list. However, the author has commented that this code block should not be used because their dataset contains categorical variables, and fitting the model to the data with categorical variables will result in an error. In this code cell, the author is creating the final k-means model with the optimum value of k, which they have determined to be 5. First, the author is creating a new instance of the k-means class with n_clusters=5. They are then fitting the model to the data using the fit function with the df_2014 dataset as the input. Finally, the author is creating a new column in the df_2014 dataset called cluster and assigning the cluster labels to each data point using the predict function. The author is then displaying the first 5 rows of the dataset to show the new cluster column. In this code cell, the author is creating a new instance of the k-means class with n_clusters=5. This means that the author is specifying that they want to create a k-means model with 5 clusters. The author is assigning this new instance of the k-means class to a variable called model. This variable will be used to fit the model to the data and make predictions. No other code is executed in this cell. In this code cell, the author is using the predict function to assign cluster labels to each data point in the df_2014 dataset. First, the author is selecting the x_scaled and y_scaled columns from the dataset using double square brackets. These columns were previously scaled using the standard scalar function. The author is then using the fit_predict function to fit the k-means model to the data and make predictions. The predicted cluster labels are being assigned to a new variable called y_predicted. Finally, the author is displaying the predicted cluster labels using the print function. In this code cell, the author is adding the predicted cluster labels to the original df_2014 dataset by creating a new column called cluster. The author is using the previously assigned y_predicted variable to add the predicted cluster labels to the dataset. Finally, the author is displaying the first 5 rows of the updated dataset using the head function. In the next code cell, the author is adding the predicted cluster labels to the original df_2014 dataset again, but this time creating a new column called cluster. The updated dataset is then displayed using the print function. In the upcoming code cell, the author will display the data on a map. In this code cell, the author is installing the Plotly library using the Conda package manager. The author is using the command conda install Plotly to install the library. The author mentions that they downloaded the library from the Anaconda prompt. This library will be used to create an interactive map to display the data. In the next code cell, the author will import the necessary libraries and create the map. In this code cell, the author is importing the Plotly Express library using the import statement and assigning it the alias px. This library will be used to create the interactive map to display the data. In the next code cell, the author will create the map using the imported libraries and the updated dataset. In this code cell, the author is creating an interactive map using the Plotly Express library and the updated dataset. The author is using the scatter_mapbox function to create the map and passing in the dataset as the first argument. The lot and lon parameters are used to specify the latitude and longitude columns in the dataset. The center parameter is used to set the center of the map to San Francisco. The zoom parameter is used to set the initial zoom level of the map. The opacity parameter is used to set the opacity of the map. The mapbox_style parameter is used to set the base map of the map. The color parameter is used to specify the column to use for coloring the data points on the map. The title parameter is used to set the title of the map. The width and height parameters are used to set the size of the map. The hover_data parameter is used to specify the columns to display when hovering over a data point on the map. Finally, the author is displaying the map using the show function. In this code cell, the author is creating a scatter plot using the Seaborn library in the updated dataset. The author is using the scatterplot function to create the plot and passing in the dataset as the first argument. The x and y parameters are used to specify the columns to use for the x and y axes of the plot. The hue parameter is used to specify the column to use for coloring the data points on the plot. The style parameter is used to specify the column to use for differentiating the data points on the plot. The markers parameter is used to specify the marker style to use for the data points on the plot. The palette parameter is used to specify the color palette to use for the data points on the plot. The legend parameter is used to specify whether or not to display a legend on the plot. The title parameter is used to set the title of the plot. The zlabel and ulabel parameters are used to set the labels for the x and y axes of the plot. Finally, the author is displaying the plot using the show function. In this code cell, the author is using the Plotly library to create an interactive map. The offline.plot function is used to create the plot and save it as an HTML file with the specified file name. The figure parameter is used to specify the plot object to use for creating the map. The file name parameter is used to specify the name of the HTML file to save the map as. The auto_open parameter is used to specify whether or not to automatically open the HTML file in a new browser window. When this code is executed, it will create an HTML file with the specified file name and open it in a new browser window. The resulting map will be interactive and allow the user to zoom in and out, pan around, and click on data points to view more information. This code cell appears to be empty, so there is nothing to explain. It's possible that the author left it blank intentionally, or they may have accidentally deleted the code that was originally in this cell. Either way, we can move on to the next cell. In this tutorial, we have explored how to use Python in the Plotly library to create interactive maps. We have learned how to import the necessary libraries, load data into our program, and create a plot object to use for creating the map. We have also learned how to save the resulting map as an HTML file and open it in a new browser window. I hope you found this tutorial helpful and informative. If you have any questions or comments, please feel free to leave them in the comments section below. Thank you for watching, and happy coding!